I'm David Sanders, and I'm going to talk about global constrained nonlinear optimization. And this is going to involve symbolic modeling of the problem and then solving the problem using interval arithmetic methods. So the goal is the ambitious one of solving general nonlinear programs. In other words, minimizing a nonlinear, non-convex function f of n variables scalar valued with inequality constraints that look like c sub I of the vector x is less than or equal to 0, and I have m of these constraints that I want to satisfy. So for technical reasons, I'll only be talking about inequality constraints in this talk. And of course, we all know that first we need to actually write down the problem, which is the modeling step that usually this community does using JUMP, the JUMP language, a domain-specific language using macros in Julia. Then afterwards, we need to actually perform the optimization using a solver. Inequality-constrained global optimization has actually two parts, of course, which is characterizing the constraints and then upper and lower bounding of the global minimum value of the problem. So in this talk, I will be showing how to specify or model a problem in a different way, which is different from JUMP but related, and solve problems to give guaranteed global minimum and minimizers. And this will be done using methods from interval arithmetic. And the key point of this talk is really how to characterize feasible sets. So this is an extension of the talk I gave 2 years ago at JUMP Dev on unconstrained optimization, and it's still a work in progress. And I'd like to point out that symbolics.jl, which is this recent library that was released for performance symbolic manipulation in Julia, really plays a fundamental role in most of this work. Just to mention some related Julia packages for guaranteed global optimization, Iago.jl is a pretty extensive global optimization package using convex and concave McCormick relaxations. Alpine.jl also uses convex relaxations, and both of these call out to external solvers. So for unconstrained optimization, there's Charybde Optim and interval optimization.jl that I've been involved with. Charybde is particularly interesting because it combines interval methods with heuristic methods. This current talk is about extending interval optimization to constrained global optimization of nonlinear problems. So I'd like to start off by showing how we can model optimization problems using symbolics in a similar way to JUMP. So this is actually a new interface for specifying and solving both constraint satisfaction problems and optimization problems based, as I said, on symbolics.jl. And the reason that we ended up going in this route is that we actually need symbolic expressions later on to run these interval-based solution methods. Of course, JUMP solves this problem by using macros. We wanted to go a different route and avoid macros as much as possible and actually work with real symbolic expressions that we can manipulate mathematically. And I just should mention that I have a related talk on discrete problems, a JuliaCon talk on Boolean satisfiability, and the future idea will be to combine all these into a unified interface. So let's start off by seeing what kind of structure this modeling language has and the solutions have. This symbolics.jl allows me to define variables using this @variables macro. That's the only macro I'm going to use, and it's just a convenience to define these symbolic variables. So x is a symbolic object which I can refer to and manipulate. So if I do x plus y, I actually get a symbolic expression back. And so we're going to use these symbolic expressions to specify all of the pieces of our optimization problem. So what does a constrained optimization problem consist of? Well, it has some variables, which is a vector of symbolic variables, has an objective function, which is, again, going to be an expression, symbolic expression, and we're just going to assume minimization for simplicity. And it has a set of constraints, which I'm going to write as a vector of symbolic expressions. And finally, it has a domain, and this is going to be an interval expression. So -10 defines an interval which represents all the real numbers between -10 and 10. And then when I take the Cartesian product, I get a box in 2 dimensions since I have 2 variables. And so this is a new type that I'm introducing that will be in interval optimization, constrained optimization problem. It receives these symbolic objects and actually converts them into algorithms that compute these sets, as I'll show later. So let's just have a look at what this looks like inside. So as I said, it stores these constraint expressions and then converts them into these objects called separators that are actual algorithms that compute with these sets. And then we solve using, for example, this minimize function. We get back a global minimum, which is an interval that is guaranteed to contain the true global minimum of this constrained optimization problem, and we get back a list of minimizers. These are boxes, in this case in 2 dimensions, and the union of these, in this case 15 boxes, is guaranteed to contain the true global minimum or minima if there are multiple minima of the same height. And the second argument is a tolerance. It's the size of the boxes that we're allowing in our minimizers list. And so we can actually plot the solution. So we're plotting here the feasible region in blue, the region defined by these constraints, and then this red dot is a set of boxes that are enclosing the global minimum. And I've actually increased the size so that they're actually visible on this plot. So let's look at a more complicated example, which shows how using the symbolics tools allows us to actually set up each part of the problem separately. So we have variables called P1 and P2. Now we're defining a standard Julia function, which is going to be our objective function. But the first thing we're going to do is actually trace through it with symbolic variables. So I'm just passing these symbolic variables into this generic Julia function. And we see that this symbolics package just recovers the structure of the expression as a symbolic expression. And that's what we're actually going to use when we set up our optimization problem. Here is the domain for this problem, and here are the constraints. And again, we can look at them and we get the nice LaTeX rendering just like in Jump. So here's a different way to actually set up the constrained optimization problem. We're just passing in these symbolic objects that we already created, the set of variables, the objective function, the constraints, and then the domain, which is this interval box. And again, we solve it with the minimize function, and we get that, in this case, 2 global minima. These are symmetrically placed global minima, and there's only one active constraint in this particular problem. And so what we see is actually we have a set of quite a few boxes that cluster around the global minimum. This is a standard effect in these kind of interval optimization algorithms, and there are ways to mitigate the fact that we have this cluster of boxes that is difficult to get rid of. Let's look at these interval methods for optimization. How do they work? First of all, why do we even need them? We know that standard numerical methods, so for example Newton, gradient descent, work well to find local minima, but they can never guarantee whether they have found the global minimum of a problem. And if we really want the global minimum, then we have to use other methods. And interval methods is one of the only classes of methods which allow us to actually guarantee in a rigorous way that we have found the global optimum or optima of a problem. And to do so, they compute with all points in a continuous set, for example an interval, simultaneous. And they can tell us something about all those points at once. And in this way, they are actually able to rigorously exclude a whole region from the search space where we can prove that the global minimum does not occur. So the way that interval arithmetic achieves this is as follows. The goal of interval arithmetic is to cheaply compute the range of a function. By the range of a function, I just mean the set of all possible values that that function can take over inputs that lie in the set of interest. Finding the exact range is actually equivalent to global optimization. It would be finding the true global minimum and maximum over the set. And of course, that's a very difficult problem. It's NP hard. So instead, what we do is ask for something weaker, which is that we ask for an overestimate, a set that encloses the true range. And we do this by defining an interval version or interval extension of the function f, which acts on intervals. As I said, an interval is all real numbers between a and b, and is represented by its endpoints a and b. How can we actually do that? Well, we're going to define functions on intervals as follows. For example, for monotone functions, exponential of the interval from a to b is the interval from exponential of a to exponential of b. That is going to contain exponential of little x for all little x in the interval a to b. Similarly, for addition, ab plus cd is the interval a plus c to b plus d. That again contains all the possible pairs of sums of values from each interval. And these functions are all implemented in interval arithmetic. Of course, for non-monotone functions it's more difficult to implement, but it can still be done. What this actually ends up giving is that for a composite function f made of several of these functions, f of x is an overestimate of the true range of the function. In higher dimensions, boxes, rectangles, hyperrectangles in Rn are vectors of n intervals representing their Cartesian product. So here's an example. We have the Cartesian product of the interval 1 to 2 times the interval 1 to 2. That's a rectangle, a square in this case, in 2 dimensions. And if we have a function of 2 variables, we can just apply that function to this interval, and that will give us an interval that contains, again, the true range of this 2-dimensional function over that input set. One of the reasons that we need interval arithmetic, or that interval arithmetic is interesting, and not only for these global optimization methods that use interval arithmetic, but actually it can be of more general interest because we can actually use it to characterize constraint sets. So it's very possible, I would be very interested to hear of applications in other optimization algorithms that need to characterize constraint sets in this way. So let's think about what a constraint actually does. A constraint like c of x less than or equal to 0 defines a set S in a declarative way, but implicitly. So S is the set of all those points x such that c of x is less than or equal to 0. And of course, we're used to checking single vectors x to see whether they lie in the set or not by just evaluating this expression. But the point is that interval arithmetic actually gives us a way to answer this question for a whole box x, for example, this rectangle that we just defined. We can ask, does the whole box x lie inside or outside the set? So here's an example. My constraint is x squared plus y squared minus 1 is less than or equal to 0. I can define that symbolically. And then I'm going to define 3 sets and ask whether they lie inside or outside this constraint set. So here's a picture. My constraint set is given by this blue disk, and the 3 rectangles are boxes, which I would like to know, are they inside, are they outside, or are they partially inside and partially outside the set? So I can use interval arithmetic to just answer that question immediately for the sets y1 and y2 that are completely inside and completely outside. We see that c of y1 lies indeed completely below 0. We can say, for example, is c1 intersect minus infinity to 0? That gives us y1 back. I can actually test, is that equal to c of y1? And it is. That means that everything lies inside the set. Similarly, I can check the intersection of cy2 with the inequality of interest, and that gives me the empty set. That means that it lies completely outside. Of course, if I try either of these with y3, we'll realize that it is neither completely inside nor completely outside. So what do we do with a box like that? Well, we can detect that part of it is inside and part of it is outside, but we don't know which part is inside or outside. Can we actually calculate that? Of course, a simple method to do that would be to cut it into pieces and check each piece separately. But it turns out that there's a better solution. And that is using this very beautiful technique called interval constraint propagation. We're going to introduce the idea of a contractor. A contractor is an operator on boxes, on interval boxes. It takes in a box and tries to remove pieces of the box which are not contained in the set S that we're studying. So this is a contractor for the set S, C sub S. So this is the technical condition that must be satisfied. So how can we create operators that do this, that take a box X and contract them based on the set S? One beautiful solution to this is the so-called forward-backward contractor, or HC4. This produces an algorithm that gives me a contractor for a given set from the declarative constraint expression. And it does this by propagating constraints up and down the so-called computational graph of the expression. So here's a visualization of the computational graph of the expression x squared plus y squared. What we're going to do is introduce new variables at each node of the graph. And each variable is going to correspond to a set or interval of possible values of that variable. And the edges in the graph are actually viewed as relations. So, for example, if a is equal to x squared, that relates a and x in the following way. If we move forwards, we can define a as being the square of x. But we can also look at this backwards to say that the range of x, the range of the interval, the set x, can be at most as large as the square root of a. And so actually, if we have a current estimate of x, we can get a new one by intersecting the current one with the reverse function of the square function, which in this case is going to be some kind of square root function. So similarly, c equals a plus b, that's now a ternary relation, is reversed as the new value of a is the old value intersect c minus b, and similarly the new value of b is b intersect c minus a. So let's give an example. The constraint x squared plus y squared is less than or equal to 1. And so we can construct the forward-backward constructor as follows. We introduce new variables at each node in the tree. At the top, we impose a constraint. So c in this case is x squared plus y squared, which needs to be less than or equal to 1. And so we intersect it with the interval minus infinity to 1. Then on the reverse pass, we undo each of these relations going back down the edges of the tree. And what we end up with is, having started with no information that x and y are both minus infinity to infinity, so we start with the whole plane as our box, and we've contracted it down to just the box minus 1 to 1 squared. And this proves that anything outside this box does not lie in the set defined by this constraint. It's a really powerful tool. So how can we automate this? I have a new package, reversepropagation.jl, that uses symbolics.jl to analyze and rewrite the expressions. For example, here we see exactly what we just did. We're starting with x and y, we're squaring x, we're squaring y, we're adding those two values, we're intersecting it with the constraint, and then we're doing these reverse functions. So if we actually use this forward-backward contractor function, we can apply it to our box y3 from before. So here's y3 as this whole initial box. And when I apply this contractor C to y3, and I contract it with respect to the output minus infinity to 1 set, I get back this purple box. And you can see that this whole green piece has been removed. So we have proved that that green piece lies outside this constraint set and can be removed. But we still don't know what it lies inside the constraint set. We want to find a piece which is guaranteed to be feasible to lie inside the constraint set. And to do that, we need a contractor with respect to the complement of this set. So we can do that as well. So here we see that y3 double prime is this set that encloses the complement of the set. So if we take the set difference of this original box with y3 double primed, we get this green piece, and that has been proved to lie completely inside the constraint set. We can formalize this in terms of what's called a separator. A separator is just a pair of contractors, one for the set itself and one for the complement. And finally, we're going to need the intersection of separators to model the intersection of sets. So given two separators representing two sets, we can actually define a separator that tells me how to contract the inside of this intersection and how to contract the outside. And in that way, we can find the feasible set of the intersection of constraints. So now we need to put all this together and include it in an optimization routine. And for that, we're going to do a spatial branch and bound algorithm. So let's start by doing that for unconstrained optimization. The point is that bounding the image of f using interval arithmetic actually gives us an algorithm for unconstrained global optimization. And that's the Moore-Skilbo algorithm, which was actually developed in the 70s, where we track an upper bound u of the global minimum through the computation. Let's see how that works visually. So here we have a function, which is x times sine of x, over some input box. And we're trying to find the global minimum of that function over that input box. What we're going to do is look at a box and do two things. We're going to evaluate the function at the midpoint of that input box. And we're going to say, does that give me a feasible point whose objective value is lower than the current upper bound? The current upper bound is this green horizontal line. For example, here we are evaluating the objective function and we find a lower feasible point. And so we're going to decrease the objective function upper bound. Once we finish processing a box, then we bisect it as I just did. And so let's see the progress of this algorithm. We've just bisected that box, and now we're looking at this box. We see that in this case, we cannot decrease the upper bound. And so we just leave the box and bisect it. And we continue doing that until we find a box like this one, where we have the interval evaluation of the function lies completely above the current upper bound, which means that the global minimum of the function cannot exist in this box. And so we can just delete it, and we carry on. And so we carry on bisecting and deleting boxes until we find the global minimum. So right now, what we see is that it looks like the global minima are concentrated around these two troughs of equal depth. But actually, now we see that over here, the algorithm has actually found a lower value and has decreased the global minimum below these local minima. And so now it will just clear up all of those boxes. And we're left with a cluster of boxes around this point. And so we know that that is the global minimum of the function over this input set. So that's how this algorithm works, using interval arithmetic in this key way to bound the objective function over an input set. And we can write the actual algorithm. This is a simple version of the algorithm written out in 20 lines or so. And that actually works for any situation. So this is just running this piece of code here on a simple scalar function. And we again find that it returns an interval containing the true global minimum and a set of minimizers. In this case, there are two of them due to symmetry, around minus the square root of 2 and plus the square root of 2. But we can also just minimize a function of two variables just as easily, and we get, again, the global minimum and the minimizers. Of course, there are many ways to improve this algorithm, and people have worked on this for a long time. There are many heuristic techniques to improve this algorithm. So what about inequality-constrained optimization? So now we just have to put everything together. We can now know how to characterize boxes as being feasible. So that is the key step that we need to add to the unconstrained optimization. In unconstrained optimization, any point in any box is feasible, but of course for constrained optimization that's not the case. And so we cannot just take the midpoint of a box and treat it as a feasible point. We actually need to search for feasible points inside each box. And so we can do that now using the separator technique. And that immediately enables us to incorporate inequality constraints into the branch and bound algorithm. So boxes in the branch and bound tree are going to be recorded as being feasible or of unknown status. And when they are feasible, we can choose points, any point in that box, evaluate the objective function there to decrease the upper bound. And that's the way in which we can produce the results that I showed at the beginning of the talk. So in summary, we have a kind of proof of concept implementation for guaranteed, constrained, nonlinear optimization in pure Julia using interval methods that works well in sufficiently low dimension. For work in progress is to improve the algorithm, improve the reliability and the speed, and in particular, try and improve the way that we're checking feasibility. Thanks for your attention.